Hey everybody, and welcome to our fifth numerical analysis lecture. This is the first lecture in which we talk about something other than root finding algorithms. Here we're going to talk about Lagrange polynomials. And here's the setup. We're given n plus 1 data points, x naught, f of x of naught, x1, f of x of 1, dot, 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 to xn f of x of n. And these data points come from an unknown function f of x. What we want to do is take these data points and construct a polynomial, we'll call it p of x, such that p evaluated at x naught equals f evaluated at x naught. P evaluated at x1 equals f evaluated at x1. So in other words, at the x coordinate of each data point, our polynomial p will have the same value as the unknown function x. At x naught, our polynomial will have the same value as f, the y coordinate of our data point. At x1, our polynomial will have the same value that f has at x of 1, our y value of the data point, and so on and so forth. And we'll make some assumptions. Just for the sake of simplicity, I don't think these have to be enforced, but just for the sake of simplicity, we'll assume x naught less than x1 less than x2. So we'll assume that the x values are in ascending order. And I mention this only because of something I'm going to talk about in just a second. We call p of x an approximating polynomial because we use p of x to approximate the values of our unknown function f of x at x values other than x naught, x1, x2, x3, and so forth. You see, we have all of these data points, x and y values. But what about the y values at x values other than x naught, x1, x2? For example, what's the value of f of x between x naught and x1? We create this polynomial, p of x, to approximate the values of f of x at values other than x naught, x1, x2, x3, so forth and so on. And I'll say for all x values, between x equal x naught and x equal x of n. So our approximating polynomial should give us good approximations for the f of x value between x naught and x1, between x1 and x2, between x2 and x3, between x of n minus 1 and x of n. And of course, if we plug in x of naught to our approximating polynomial, we want to get exactly the y value of our data point. And if we plug in x1 into our polynomial, we want to get exactly the y value of our data point, and so forth. And we will notice that we're only going to use this to get approximations for the y values of f of x between x of naught and x of n. So for any x values greater than xn, or less than x naught, we guarantee nothing. We don't guarantee that our polynomial will approximate the unknown function with any degree of accuracy or anything like that. So our approximations, we hope, are valid, but if they are valid, they're only going to be valid between x of naught and x of n. What goes on outside of that interval, we're not really going to hope to get very good results. And why? Well, maybe we'll talk about that later. Note well, we mentioned this before, but we just want to emphasize this point again. In our attempt to force p of x to closely approximate our unknown function f of x, we will construct our polynomial p of x in such a way that p of x agrees with f of x at all data points. So in other words, p evaluated at x of I equals f evaluated at x of I for I equals 0, 1, 2, 3, all the way up to n. Or said differently, like we had written before, p of x naught equals f of x naught, p of x1 equals f of x1, and so forth and so on. We could at least require that our polynomial p of x has these characteristics. If our polynomial doesn't even agree with the unknown function at the data points, how good can it be, right? So we require that our approximating polynomial agrees with f of x at all of the data points. Given the data points, x of naught, f of x of naught, x of 1, f of x of 1, x of 2, f of x of 2, and so forth, x of n to f of x of n. We define the Lagrange polynomial of degree n to be given by the following. And before we look at this too closely, let me point a few things out, okay? Just exactly how many data points do I have here? How many data points do I have here? And we might say n and we'll be close, but we won't be quite right. Notice if we start at this data point, we have 1, 2, 3, 4, 5, all the way up to n. So starting here and going here, we have n data points, but we didn't count this one. This will be the n plus first. So we have n plus 1 data points. And from our n plus 1 data points, we're going to get a Lagrange polynomial of degree n. And here's sort of what it looks like. It looks like some function, L sub n sub 0 evaluated at x, times f of x naught, the y coordinate of the 0th data point. And then we have another function, L sub n sub 1 evaluated at x, times f of x of 1, the y coordinate of the first data point. And then we have some function L sub n sub 2 evaluated at x, times f of x2, where f of x2 is the y coordinate of the second data point. Dot, 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 some function L sub n evaluated at x times f of x of n, the y coordinate of the nth data point. So in other words, we have the y-coordinate of the 0th data point, f of x naught, with some function of x as a coefficient. The y-coordinate of the first data point, f of x1, with some function as its coefficient. F of x sub 2, the y-coordinate of the second data point, with some function of x as its coefficient, and so on and so forth. And notice that the first subscript of all of these functions is n. N sub l comma 0, n sub l comma 1, n sub l comma 2, n sub l comma n. So the first subscript of all of these functions is n. We'll see why in a couple of minutes. The second subscript matches the subscript of the y value of the data point. So we have L sub n sub 0, L sub n comma 0 of x times f of x sub 0. L sub n sub 1 L sub n comma 1 of x evaluated at f of x of 1. So notice this, 0 pairs up with 0, 1 pairs up with 1, 2 pairs up with 2, n pairs up with n. So the second subscript matches the subscript of the x value that f is evaluated at. Now let me say a little bit more about what each of these functions, L sub n sub whatever, are. Okay, here's how the ith Lagrange coefficient is defined. And maybe I should just call it that. So this coefficient would be multiplied by f of x sub I. Let's see if we can discern a pattern. X minus x0, x minus x1, dot, 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 all the way up to x minus xi sub 1 times x minus xi plus 1. Did you notice that? Right here, we're missing one factor. We're missing x minus x sub I. It's not up here. We go from x minus xi minus 1 to x minus xi plus 1. And then we keep on going until we reach the end, x minus x sub n. So in the numerator, we're missing the factor x minus x sub I. We have x minus x0, x minus x1, and so forth. We have all of those. As far as the numbers from 1 to n, or the numbers from 0 to n, we're missing x sub I deliberately. Let's see what we have on the bottom. xi minus x0. Well, let's see. Up top we have x minus x0. On the bottom we have xi minus x0. Up top we have x minus x1. On the bottom we have xi minus x1. So whatever x coordinate is here, we have down here x0, x0, x1, x1, xi minus 1, xi minus 1, xi plus 1, xi plus 1, xn, xn. And where we have an x up here, we have an xi down here. X, xi, x, xi, x, xi. Well, no wonder we're missing x minus x sub I up here. Could you imagine what would happen if we follow this pattern top and bottom and we had the xi factor? That we'd have x minus xi on top and xi minus xi on the bottom. Oops, that's 0. Well, no wonder we had to omit that. So this is how the ith Lagrange coefficient is defined. And in general, the ith Lagrange coefficient is multiplied by the y-coordinate of the ith data point. Down here we have the zeroth Lagrange coefficient multiplied by x multiplied by f of x of 0. Here we have first Lagrange coefficient multiplied by f of x of 1. Here we have the second Lagrange coefficient multiplied by f of x of 2 and so forth. So this sort of explains the second subscript. The second subscript tells us which Lagrange coefficient this is. This is the zeroth Lagrange coefficient. It multiplies f of x naught. This is the first Lagrange coefficient. It multiplies f of x of 1. This is the second Lagrange coefficient. It multiplies f of x of 2 and so on. So we sort of know what the second coefficient of the Lagrange, we sort of know what the second subscript of the Lagrange coefficients represents or refers to. The first coefficient of the Lagrange, the first subscript of the Lagrange coefficient is n in each case. Well, what's that about? Note well, how many of these factors do we have up top? We go from x0, x1, so forth and so on, all the way to xn. And that would be n plus 1 factors, except we're missing x minus xi here. So we have n factors up here. And notice, each factor is of the form x minus a constant. If we take n factors of x minus a constant and multiply them all together, like we're doing up here, what are we going to get? Aren't we going to get a polynomial of degree n? And that's exactly what this represents. It tells us this Lagrange coefficient is a polynomial of degree n. Now let's take a break for technical details for a minute or two. And let's just write out not the ith Lagrange coefficient like I have up here. I'll keep this up here to use as a model. But let's write the zeroth Lagrange coefficient, and the first Lagrange coefficient, and the second Lagrange coefficient. Not using constants, but using real numbers so that we can see how this works. Let's do the 0th Lagrange coefficient of degree n. And we'll use our model as reference. Up top, we have x minus x0, x minus x1. We have x minus the x coordinate of every data point except x of I. Well, what is I in this case? It's 0, isn't it? So the factor that's going to be missing up top is going to be x minus x0. We're not going to have an x minus x0 up top. So we'll have x minus x1, x minus x2, dot, 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 x minus x sub n. Then what do we have on the bottom? Whatever this is, whatever I is, we have x of I minus whatever this is. Okay. Let's not worry about I yet. Notice that this matches this. Whatever this is up top, that's what we have down here. So x1 here, they match. x2 here, they match. xn here, they match. Okay. What goes here and here and here? Notice in our model, it's the same thing. xi, 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 where I is this subscript. Here's our I down here. I is 0. So we're going to have x of I where I is 0. Okay. Yeah, let's give us a little more room. And up top, we got x minus something, x minus something, x minus something, dot, 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 x minus something. And in our model, we have x minus x0, x minus x1, dot, 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 x minus xi sub 1, x minus xi plus 1. The only factor that's missing here is x minus x sub I. So the only factor that's going to be missing up here is x minus x sub 1. So we're going to have an x minus x0. And we go here and say x minus x1. Oops, no. We don't have an x minus x1, so I guess x minus x2, x minus x3, x minus xn. And on the bottom, we fill in, like we did in the previous example, that we noted that in each factor, the second term top and the second term bottom are the same. x1, x1, x2, x2, xn, xn. So whatever this is up top, that's what we have down in the bottom. Minus x0, minus x2, minus x3, minus xn. Now what goes here? when we have the ith Lagrange coefficient, xi goes first in the bottom. Xi is the first term of each factor in the bottom. Xi, 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 xi. This is the first Lagrange coefficient, so x1 is going to go first. x1, 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 x1. So that's the pattern. And let me do one more. We'll do the nth one. And up top we have x minus x0, x minus x1. The only factor that we leave out is x minus xi. What's I here? Here's our I equals n. So the factor that we're going to leave out up top is going to be x minus xn. We're not going to have it up here. But we will have x minus x0, x minus x1, x minus x2, dot, dot, dot. We're leaving out x minus xn, so the last factor up here will be the factor that comes before x minus xn, which is x minus x of n minus 1. That's what the top looks like. And now we fill in the bottom. And we remember that in each factor, top and bottom, the second term is the same. X naught, whoops, whoops, whoops. X of 1 here. X naught, x1, x1, x2, x2, x of n minus 1 up top, x of n minus 1 on the bottom. Now what goes here? We look at our model. This is the ith Lagrange coefficient, and x of I goes first in each factor. Well, down here, this is the nth Lagrange coefficient, so x of n goes first. Now, this seems like almost a whimsical kind of construction. It seems very complicated. And although there's a pattern, it doesn't seem to serve any purpose. But let's just see what happens. Let's take this Lagrange coefficient and plug in x sub 0. I'll tell you what. Let me write it this way. I'm going to plug in x sub 0. So every place that I see an x on top, I'm going to plug in x sub 0 instead. Watch what happens. That's what we get up top. And on the bottom, these are all constants. There's nothing to plug in. We just write these down verbatim. And look at the factors up top, and look at the factors in the bottom. Son of a gun. The factors up top are exactly the same as the factors in the bottom when we plug in x of 0 into the zeroth Lagrange coefficient. And we're going to get, son of a gun, 1. When we plug x of 0 into the zeroth Lagrange coefficient, we get 1. Huh. Now let's try this again. We'll work with the zeroth Lagrange coefficient again. But this time, let's plug in x of 1. The x value of some other data point. The x value of some data point other than x of 0, f of x of 0. And let's see what happens. Whoops. I'm going to take the zeroth Lagrange coefficient, and I'm going to plug in x of 1 for x, and let's see what happens. Whoops. The zeroth Lagrange coefficient evaluated at x of 1, and watch what happens. Whoops, x of 1. When I plug in x of 1, the x coordinate of a data point other than the zeroth data point, what's this right here? X of 1 minus x of 1 equals 0. So the whole thing is 0. Well, wait a minute. What? I plugged in x of 0 and I got 1. Now I plug in x of 1 and I get 0. I wonder what would happen if I plugged in x of 2. Let's try that. We're going to plug in x of 2. if I plug in x of 2 for x, notice what happens. No problem here. Oops, it happened again. It happened right here. And I am going to get 0 again. One of those factors is 0, so the entire numerator is 0. I'll be a son of a gun. Do you see what's going on here? You probably do, because even I understand it now. And I guess if I can understand it, anybody could. And do we see what's going on enough to speculate what the pattern is here? I think we do. I think we do. So let me write down what the pattern appears to be. We took this thing and plugged in 0 and we got 1. Those two match. We plugged in 1, we plugged in x of 0 and we got 1. We plug in the x coordinate of any other data point. Oops. We get 0. So if we take the x coordinate of any data point other than the 0th data point and plug it into the 0th Lagrange coefficient, we get 0. If we plug x0 into the 0th Lagrange coefficient, we get 1. Well, I wonder if the same kind of thing happens with the first Lagrange coefficient and the second Lagrange coefficient. Probably the same thing happens, but let's just check and see. X minus x0. Here is our first Lagrange coefficient. And since the subscript here is 1, let me plug in x of 1 and see what happens. X of 1. And you know what? I plug in x of 1 into the first Lagrange coefficient, and the factors up top are exactly the same as the factors at the bottom. So what's this thing going to be? It's going to be 1. When I plug x of 1 into the first Lagrange coefficient, in other words, when this subscript and this subscript match, I get 1. Now, what happens if I plug the x-coordinate of any other data point into this thing? When I plug in x of 1 into the first Lagrange coefficient, I get 1. Suppose I plug in the x-coordinate of some other data point. Let's say that I plug in x of 0. 0, 0, 0, 0. Sure enough, the very first factor up top equals 0. So if I plug in the x-coordinate of a data point other than the first data point here, son of a gun, I get 0. If I plug in x of 2 here, I'm going to get 0. If I plug in x of n here, I'm going to get 0. If I plug in x of 1, a subscript that matches this thing, I get 1. But if I plug in the x value of any other data point, I get 0. And this sort of thing happens for all of the Lagrange coefficients. We can extend this pattern to the Lagrange coefficients in general. And that's what we're going to write down right now. If I and j are the same thing, then we're going to get 1. But if I and j are different, we get 0. So if we take the x-coordinate of a data point and plug it into a Lagrange coefficient, and these subscripts match, we get 1. If we plug the x-coordinate of a data point into a Lagrange coefficient, and these subscripts don't match, we get 0. And that's going to be really, really important as far as how our Lagrange polynomials behave. Let me break for just a second, and we'll see how the big picture unfolds. Okay, this sort of takes us to a quick summary of what we've established. Given n plus 1 data points, x0, f of x0, x1, f of x1, x2 f of x2 dot 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 xn f of xn. The Lagrange polynomial of degree n is given by this expression. The zeroth Lagrange coefficient times f of x0, the first Lagrange coefficient times f of x1, and so on. And the ith Lagrange coefficient, L sub n comma I of x, is this expression. And notice again what we observed earlier. In the top we have n factors going from x0 to xn with x minus xi omitted. So in other words, we have n factors, each of them of the form x minus a constant. So the numerator of this thing is the product of n factors of the form x minus a constant. The numerator of this expression is an nth degree polynomial. Now, what does the denominator look like? We have constant times constant times constant times constant times constant. Oh, the bottom's just a constant. So we have an nth degree polynomial divided by a non-zero constant. This whole thing is a polynomial of degree n. Now, let's put into practice the observations that we made just a couple of minutes ago. Oh, wait a minute. I do need to say something else. This is the ith Lagrange coefficient. And the ith Lagrange coefficient is a polynomial of degree n. So let's see what we have as far as our Lagrange polynomial of degree n is concerned. Polynomial of degree n times a constant is a polynomial of degree n. A polynomial of degree n times a constant is a polynomial of degree n, and so on and so forth. So what do we have? Polynomial of degree n plus a polynomial of degree n plus a polynomial of degree n plus a polynomial of degree n. When we add a bunch of polynomials of degree n together, what do we get? A polynomial of degree n. So that's why we call this the Lagrange polynomial of degree n. It literally is, when we add all of these things up, it literally is a polynomial of degree n. Now, let me erase this monstrosity. We're not going to look at it for a while. But let's put into practice what we just saw a few minutes ago. P evaluated at x0. Let's see, that's going to be the zeroth Lagrange polynomial evaluated at x0 times f of x0. Then we're going to have the first Lagrange polynomial evaluated at x0 times f of x of 1 plus the second Lagrange polynomial evaluated at x0 times f of x of 2 plus the nth Lagrange polynomial evaluated at x0 times f of x of n. These two subscripts match. So this is equal to 1. These two subscripts don't match. This is equal to 0. These two subscripts don't match. So this is equal to 0. These two subscripts don't match. So this is equal to 0. Son of a gun. This term is 0. This term is 0. This term is 0. This term is 1 times f of x 0. So you know what? That we have p evaluated at x0 equals f of x0, just like we want our approximating polynomial to do. We want our approximating polynomial evaluated at x of 0 to equal the y coordinate of the 0th data point, and it does. Well, was that just coincidence, or will it happen in other cases too? Let's see. I'm going to erase some of this. Maybe that was just a wild coincidence. Let's plug in an x coordinate of another data point. Let's say x of 1. Let's plug in x of 1. X of 1, x of 1, x of 1, x of 1, x of 1. Now let's see what happens. These two coefficients are different. Oops. So this is going to be 0. Now in the second term, these two coefficients are equal. So this is going to be 1. In the next coefficient, these two subscripts are different. This is going to be 0. Over here, these two subscripts are different. This is going to be 0. So this is 0, this is 0, and this is 0. The only term that's not 0 is this one. And it's equal to 1 times f of x of 1. And son of a gun, it happened again. We take x of 1 and plug it into our Lagrange polynomial, and we get f evaluated at x of 1. When we plug x of 1, the x coordinate of our first data point, into the polynomial, we get the y coordinate of our first data point, f of x of 1. You know what? This Lagrange polynomial seems to be doing exactly what it's supposed to do. Let's do one more. Let's try plugging in the x coordinate of another data point. Let's say x of 2. I'll plug in x of 2. And let's see what happens. These two subscripts don't match, so this thing is 0. These two subscripts don't match, so this thing is 0. These two subscripts do match, so this thing is equal to 1. These two subscripts don't match, so this thing is equal to 0. Every term is equal to 0, 0, 0, 0. except for this term. And this term is equal to 1 times f of x of 2. And son of a gun, it happened again. We plug the x-coordinate of a data point into our polynomial, in this case, x of 2, and we get the y-coordinate of the data point. So you know what this means. Our Lagrange polynomial constructed in this fashion agrees with the unknown function f of x at all of the data points. Now, let me answer a question that you might be asking. And you might be wondering this. Does this mean that if I plug in any x value, let me erase first and talk and think later. Let's say that I pick an x value, and this x value that I'm plugging in is not equal to the x value of any of the data points that we have. Does that mean that this is going to be 0, and this is going to be 0, and this is going to be 0, and this is going to be 0? No. These Lagrange coefficients become 0 exactly when we plug in an x value of a data point whose subscript does not match the subscript of the Lagrange coefficient. So if I take an x value that doesn't happen to be the x value of any of the data points, and I plug it in, this thing is not going to be 0. 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 And what I'm going to get, hopefully, is approximately the value of the unknown function at this value x. Now, the only x values that make our Lagrange coefficient 0 are the x values of the data points whose subscripts don't match the subscripts of the Lagrange coefficient. Now let's see if we need to do more theory or if we need to do an example. Okay, 3 data points. -1, 0, 1, 2, 2, 9. x0 is -1, and f of x0 is 0. x1 is 1, and f of x1 is 2. x2 is 2, and f of x2 is 9. We have 3 data points. We want to construct the Lagrange polynomial of degree 2. Is that right? Yeah. If we have n plus 1 data points, then we have a Lagrange polynomial of degree n. Okay, cool. I guess the thing to do is to construct our Lagrange coefficients. And let's say this is the zeroth Lagrange coefficient, so we leave out x minus x0. So we'll have x minus x1 and x minus x2 all over x0 minus x1, x0 minus x2. Let's see, does that work? These are the same. These are the same. And up top, we're missing x minus x0. Yeah, I think we're good. So x minus x of 1, I'm sorry, yeah, x minus x of 1, so x of 1 is 1. X minus x of 2, you know what, let me just write down x0, x1, x2, so that I don't do something stupid. X minus x1, that's 1. X minus x2, that's 2. And then we have x0, which is negative 1, minus something. And let's say, these two things match, don't they? So, minus 1, minus 1, minus 2, minus 2. Okay. Then we have plus 1 times plus 2. And up top we have x squared minus x minus 2x plus 2. So that's our first approximating polynomial. Our second, the subscript is 1 here, and maybe I should say this is our 0th polynomial. This is our first. So we leave out x minus x1 here. So we'll have x minus x0, x minus x2. And since the subscript is 1 here, we'll have x1 minus whatever, x1 minus whatever. And whatever goes here up top goes here on the bottom. Whatever goes here up top goes here on the bottom. Okay, everybody, let's fill in the blanks. You have x minus something, x minus something. Let's see. X of 0 is negative 1. So x minus a negative 1. And x2 is 9. So x minus 9 up top. And whatever goes up top here and here repeats on the bottom. And we have x1 here and here. What is x1? x1 is 1, okay. 1 minus, whoops. Let's see, x minus 9, so that's 1 minus 9. X minus a negative 1, that's 1 minus a negative 1, okay. And on the bottom, I get 2 minus 8. So we got a negative 16 on the bottom. And up top, we have x plus 1 times x minus 9. So we have x squared plus x minus 9x is minus 8x minus 9. That's our second Lagrange coefficient. And let me make sure that this makes sense. And I think I'm wrong somewhere. Let's see. You know, I don't like what I have here. Let me make sure I haven't messed up. Oh. Okay. Hang on a sec. Let me check and make sure I've done everything right. Okay, I think I see my problem. This appears to be correct. If I plug in x of 0 into this zeroth Lagrange coefficient, I should get 1. Do I? Here's x of 0, negative 1. What happens when I plug it in? Negative 1 squared is 1. Minus 3 times a negative 1, so that's 1 plus 3 is 4. Minus 2 is 2, so we get 2 over 2, which is 1. When x equals x0, this thing is 1. That one looks fine. Here's the one that bothered me, and for good reason. This is not right. I'm supposed to have x2 here and here. x2 is 2. I plugged in the y coordinate, not the x coordinate. So, yeah, what should go here is 2. Now maybe this will make a little bit more sense. And let's see, if I plug in x of 1, if I plug in x of 0, this will be 0, the whole thing will be 0. If I plug in x of 2, this will be 0, the whole thing will be 0. And if I plug in x of 1, I should get 1. Let me multiply this junk out. And what I should get is 2 times negative 1. So I should get a negative 2 on the bottom. And on the top, I should get x squared plus x minus 2x is minus x. 1 times negative 2 minus 2. Now again, let me make sure it works. If I plug in x0, since the subscripts don't match, I should get 0. So I plug in negative 1 and I get negative 1 squared is 1. Minus a negative 1 is 2, minus 2 is 0. Good deal. Suppose I plug in x of 2. The subscripts don't match, so I should get 0. If I plug in 2, I get 4. Minus 2 is 2, minus 2 is 0. Beautiful. What happens if I plug in x of 1? If I plug in x of 1, the subscripts match. I should get 1. So I plug in 1 and I get 1. Minus 1 is 0. That leaves me with minus 2 over minus 2, which is 1. Perfect. Okay. I apologize for the mistakes, but I'd rather catch them here than wait till I get to the end of the exercise and discover something's not right. Now we have one more Lagrange coefficient to do. And the subscript here is 2. So x minus x2 is going to be missing up top. We'll have x minus x0, x minus x1. And on the bottom, we'll have x2 minus x0, x2 minus x1. Okay, I'll plug in x0, which is negative 1. So x minus x0. And on the bottom, I'm going to have x2, which is 2, minus x0, negative 1. Here I have x minus x1. x1 is 1. So x minus 1. And 2 minus x of 2, which is 2, minus x of 1, 1. And let's see what I get. This is going to be x plus 1 times x minus 1. This is going to be plus 2 times 1. Okay. So we should get x squared minus 1 up top and 2 on the bottom. Let me check it out. This is the second Lagrange coefficient. So for x0, this should be 0. I'll plug in negative 1. Let's see what I get. Negative 1 squared is positive 1 minus 1 is 0. Beautiful. Okay. If I plug in x of 1, I should get 0 also. I plug in 1, I get 1 squared is 1 minus 1 is 0. Looks good. And if I plug in x of 2, since this is the second Lagrange coefficient, since I plug in x of 2, I should get 1. So let's see. Oops, I don't like this. I don't like this at all. 2 squared minus 1 is 3 over 2. Yuck. Okay, I don't like that. The top looks fine, I think. But the bottom, I think there's a problem with it. Forgive me, I'm having a duh moment. This is 2 minus a negative 1, not 2 times a negative 1 or anything like that. So forgive me, this should be 3. Beautiful. Now when we plug in x of 2, we get 2 squared minus 1 is 3. Over 3 is 1. So when we plug in x of 2, we get 1 just like we should. Okay? We've got our Lagrange coefficients. Let me tidy things up a little bit. Okay, let's see how this shapes up. Our Lagrange polynomial of degree 2 is going to have the 0th Lagrange coefficient times f of x of 0, the first Lagrange coefficient times f of x of 1, the second Lagrange coefficient times f of x of 2. Okay, the 0th Lagrange coefficient, that's this polynomial, times f of x of 0 is 0. And let me write f of x of 0 here, just so we know where we're getting these things. Okay, that's better. So the 0th Lagrange coefficient, that's this thing, times f of x of 0, which is 0. The first Lagrange coefficient, that's this thing, times f of x of 1, which is 2. And the second Lagrange coefficient, that's this thing, times f of x of 2, which is 9. 0 times this thing, all this gets wiped out. But I guess what that means is it was just extraneous information or superfluous information. Negative 2 times 2 is negative 1, so negative 1 times the numerator, negative x squared minus a negative x is plus x, minus a negative 2 is plus 2. And then we have 9 divided by 3 is 3, so it's 3 times this numerator, 3x squared minus 3. And combining all of this, negative x squared plus 3x squared is 2x squared. We have an x here, no x here. And 2 minus 3 is negative 1. So this is our Lagrange approximating polynomial when simplified. Now, does it agree with all of the data points? Let's see. P of 0 is 2 times 0 squared plus 0 minus 1, which is minus 1. I'm sorry, that's not one of our data points. P of x of 0 is P of negative 1. So we'll have 2 negative 1 squared plus negative 1 minus 1. So we have 2 minus 1 is 1, minus 1 is 0. So x0 is negative 1, and P of x0 is 0, which is what f of x0 should be. Check there. P of x1, so that's P of 1, so that's 2 times 1 squared plus 1 minus 1 equals 2 plus 1 is 3 minus 1 is 2. So P of x1 is 2, and that's exactly what f of x1 is, okay? And P of x2. x2 is 2. 2 squared is 4 times 2 is 8, plus 2 is 10, minus 1 is 9. P of x2 is equal to 9, and that's what f of x2 is. Okay, beautiful. We have created a Lagrange approximating polynomial, and it works. Now, before we part company, I have a few parting comments to make. I guess the first thing that I want to point out is we'll use Lagrange polynomials when we expect the unknown function to be well behaved and not erratic. We expect the graph of the unknown function to be a nice, kind of smooth, gently rolling up and down function. And who knows, maybe the function looks something like this. And it fits our data points. Maybe this is what the unknown function looks like. And our Lagrange polynomial, being a polynomial, is probably going to look kind of like this. And if we expect the unknown function to be well behaved, not a screwball function, the Lagrange polynomial will probably approximate it very nicely, especially if we have a lot of data points. Here's the thing, though. A set of data points doesn't necessarily uniquely identify the unknown function. This is what the unknown function could look like, but the unknown function could also look like this. The function that I've drawn in red passes through all of the same data points, but it doesn't look like the first function. Our polynomial will probably look very much like the first function, not a screwball function. What we have in red is a pathological function. It's erratic. It's going up and down, and if we don't know or expect that our function could look something like this screwball function, this erratic function, maybe Lagrange polynomials aren't the way to go. But if we have reason to believe that maybe the unknown function is sinusoidal, or maybe a polynomial itself, maybe the unknown function is a polynomial, or maybe the unknown polynomial is logarithmic or exponential, like e to the x. Nice, well-mannered functions. Lagrange polynomials are the way to go. And they'll probably give us a very good approximation to the unknown function, just as long as we have no reason to believe that the function is erratic and not well behaved. There's something else that we need to emphasize about Lagrange polynomials and approximations, and that is that we only intend for it to approximate the unknown function on the interval from x0 to xn. Let's take a look at our approximating polynomial, which I have drawn in black, and the unknown function, which is in red. And on the interval from x0 to xn, the approximating polynomial very closely approximates the unknown function in red. And outside of the interval, the unknown function just sort of gently rises and falls and rises very gently. But outside of the interval, the Lagrange polynomial is not going to do that. Think about this. A polynomial of degree n, as n goes to infinity, what happens to an approximating polynomial of degree n? And let's just say that the lead coefficient, the coefficient of the term of degree n is positive. We have an approximating polynomial of degree n, and the coefficient of that nth degree term is positive. As n goes to infinity, what's going to happen to that polynomial? Well, between x0 and xn, the data points are forcing this polynomial to conform to the y values of the data points. But outside of this interval, there's nothing constraining the Lagrange polynomial. It's a polynomial of degree n, lead coefficient is positive, and as n goes to infinity, very quickly, this polynomial is going to take off to infinity like the proverbial bat out of hell. And the same kind of thing is going to happen as x goes to negative infinity. If the lead coefficient is positive, and if n is even, as x goes to infinity, this thing's going to go to infinity like the proverbial bat out of hell. If the coefficient is odd, then we're going to have a positive number times x to an odd power. And as x goes to negative infinity, this thing is going to head down to negative infinity. Again, like the proverbial bat out of hell. So only between x0 and xn do we consider our Lagrange polynomial to be a legitimate tool for approximating the unknown function. Outside of the interval from x0 to xn, hey, this thing's going to go to positive infinity and over here to negative infinity or positive infinity. And the unknown function may continue to meander like this. So outside of the interval from x0 to xn, the Lagrange polynomial cannot be trusted to be a good approximation of the unknown function. We only rely on it to approximate the unknown function between x0 and xn.